Okay, everybody, so this is the famous sign problem, and it usually goes a little something like this. So you're a small business owner, and you have a shop in an alleyway, and you put up this hanging sign that your friend made for you, but it weighs a little bit. It's 500 kilograms. Now, you were able to get the highest or the strongest rope they had in the hardware store could hold 3,500 newtons. So the rope can withstand 3,000, let's write that down, 3,500 Newton max, okay? That's the tensile strength max, and we'll put max right there too, okay, of your rope. And you think, well, that shouldn't be too bad of a problem. You're going to use two pieces, doubling up. That's, 7,000 newtons. That should be plenty to cover this 500 kilogram sign. But then, because the alleyway is a little odd and you can't just attach the rope anywhere, your angles end up at a slightly odd place. One of them ends up at 22 degrees. The other one ends up at 53 degrees. And so you need to figure out if your sign will actually be supported by your ropes, if you can keep it nice and level and steel like this. And so you could just go to hang it and possibly crush somebody if it doesn't work, or you can calculate it. Now, this problem scares a lot of people because they're like, oh my goodness, I have so little information. I need at least the force on this one or on that one or something like that. But what I'm going to show you is you don't. Because of Newton's third law, we can write equivalent statements. Now, I'm going to go ahead and break this down a little bit, and I'm going to assign one of these as a tension force of tension force A. The other one, I'm going to make tension force B. And both of those, we don't really know anything. Those are unknowns at this time, okay? What we do know, however, is we know that angle A theta is 53 degrees, angle B theta is 22 degrees. We know the mass is equal to 500 kilograms, and we know that gravity is going to happen on Earth, so that's going to be 9.8 meters per second squared. You should also know that gravity, and so we'll go ahead and draw gravity, acts straight down, and it's going to just be that mass times little g. And so we could actually go ahead and calculate gravity if we want, but let's hold off on that on just a second. We're going to need to know some other things. What we're going to need to know is that each of these signs, these ropes are actually going to have two different vectors that they're breaking things down into. They're going to have, that one's not A. They're going to have an X component, and they're going to have a Y component. Now, we can go ahead and assume that these are made by the same way we do all of our vector components. And so I can say that TBY is equal to our hypotenuse times sine of theta B. And the one for A is the same thing, but being multiplied by A and theta A, right? We can also say that our X is the hypotenuse cosine of its angle for both of them. I don't know why I made that one A. That's a B. Okay. So with that, we now have a lot of information, but not a lot of numbers, and that scares a lot of people real quick. But it's okay. It's okay because we can solve things. Really, if you look at all this, we only have two unknowns. We have TA and TB that are unknown. Yes, we don't truly know TBY, or TAY, or their X, but that's only because we don't know TA and TB. So what we do is we start to come up with Newton's third law equivalent statements. The first one, we know if this is going to stand up, that magnitude of gravity has to be equal to the combined y's. We also know that if it's not moving side to side, that TAX has to be equal in magnitude but opposite in direction of TBX. Now, you might at first say, well, that doesn't help me a whole lot, but I bet it will. The thing is, we need to break these down into the further things we know, aka this stuff down here, okay? So the next step is to break these into their known parts. So now I've broken both of these two equivalencies down into a further understanding of what I have, because these are variables I actually have. I actually have theta A, theta B. We know what sine and cosine are of these. I know what mass, I know what gravity is. So if you look at this, now I have these two equivalent statements, and I'm just going to label them 1 and 2. So this is 1, this is 2. And between them, there's only two variables. There's unknown variables. There's TA and there's TB. That's good, because if I only have two variables that I don't know, and I have two equations, different equations that use them, I should be able to solve for one on one and plug in the rest into the other and only have one variable. And you can solve an equation for one variable. Now, if you look at this one, it has more knowns, but it also is a little bit more complicated to isolate one of these. So the first thing I'm going to do is I'm going to isolate one of these, probably TA first, just because that looks super simple. In fact, if I divide both sides by cosine of theta A, you can see that I would cancel out on that side and end up just on that side. And so I would have a new statement of TA is equal to tension B times cosine theta B divided by cosine theta A. And that's good. That's really good, because now we can plug this value for TA into this equation, and we'll only have one variable of TB. If you're having trouble picturing what that looks like, let's just go ahead and do it. Let's use another color for it, though. Let's see, we're solving for TB. We made that one green, so let's do it in green. Okay, so now I'm going to have mg is equal to, instead of TA, I'm going to write TB cosine theta over cosine, that's theta B, over cosine theta A times sine of theta A plus TB sine theta B. Ooh, well, this is good, because if you look at this, I have this term multiplied by TB and this term multiplied by TB. So it looks like TB was distributed, so I can just pull it straight out, and I can end up with mg is equal to TB times cosine theta B divided by cosine theta A times sine theta A plus sine theta B. Now, I'm sure you're saying, oh my goodness, look at all those sine cosines. I'm sure there's some trig equivalencies we can do to narrow that down, and there might be, but why bother? If you put cosine of an angle in your calculator, you're going to get a number value. For every one of those, I can get a number value. So instead, I'm just going to go ahead and solve this as is, and say that TB is now equal to mg divided by cosine theta b divided by cosine theta a, having trouble writing down here, times sine theta a plus sine of theta b. And that's good because I can plug in all my numbers to that. After I plug in all my numbers, I now have that T of B is equal to 3,052.9 newtons. And that's part of my answer. So I'm going to go ahead and kind of box that in. All right, I'm also going to store it in my calculator. I'm going to start under B so I remember that it's saved as B. But then I'm not quite done yet. We can see where this 3,500 Newton max tension rope would withstand this side, but will it withstand the other side? Well, luckily we've already written a statement to where it's real easy to go ahead and plug in our values for that. And so we can simply just say that T of A is equal to, and now we can go ahead and plug in numbers here. And this is where it's important to remember that I went ahead and I stored this one in my calculator, so I had the exact value of it. So I'm not just guessing here. And that's a terrible decimal in 9, so I'm going to draw that a little bit better. But basically I get that it's equal to 4,703.5 newtons, which means the rope would break. But if you want to double check, you just do your equivalency statements. You use this number and this number, and you plug it in either equation 1 or equation 2 and see if they equal each other. If they don't, then you know that you did something wrong and this doesn't even work at all. But as long as these two numbers prove 1 and 2 as true statements, then you're good. And they should, as long as you did the math right. And that's how you do the crazy sine question.